Hi everyone, my name is Sylvia. I'm the marketing director at Tom Sawyer Software. Welcome to this morning's webinar, the first of two webinars to learn how to use Tom Sawyer Perspectives and Neo4j to build applications with graph visualization capabilities. In the first part, Josh will demonstrate how to connect your Neo4j database to your Tom Sawyer Perspectives schema and data model, and then use that data model to create a simple graph visualization. Heading this webinar today will be Joshua Feingold, Solutions Engineering Manager of Tom Sawyer Software. Josh leads the solutions engineering team and oversees pre-sales engineering as well as prospect and customer technical support. He's also involved in planning and working on professional service efforts and regularly travels to visit customers and attends events to demonstrate the company's graph visualization and analysis solutions. So without further ado, I will hand it over to Josh, who will now begin today's presentation.
Thanks, Sylvia. So I know that we have people here who are coming to us both from the Neo4j perspectives and from the Neo4j user base and the Tom Sawyer Perspectives user base, and people who may even be new to both. So I just want to talk a little bit about what each of those things is before we jump into it. So Tom Sawyer Perspectives is the flagship product from Tom Sawyer Software, represents basically an approach to turning data in your back end into something that you can work with and understand on your front end. It has three parts that we're going to work with today. One of them, or we're going to work with two of them today. One of them is an API level, which we will not be getting into. The other is a visual design space, which we will be working with heavily, and you will learn a lot more about as we go through. And the third is the actual front-end application, and we will be seeing a manifestation of that, which is just a preview using default layouts. Or default arrangements of our components, and you'll be seeing a lot of that as well. So keep in mind that that's what Perspectives is, basically. It's an SDK that connects your backend data and makes it visible in the front end, and we're going to be looking at some components of that today. Neo4j is a graph database. Unlike RDF, the objects inside of a Neo4j database are attributed. So you have nodes and edges, and those nodes and edges can have information associated within that object, as opposed to, in an RDF style database where each piece of information is its own node or its own edge with no additional annotations, just connections to other pieces of data. Right? So we're going to talk a lot more about both of these things and how they work together as we go on. So I'm just going to kind of leave the overview at that. And we'll see details as we go. So today, if you download Tom Sawyer Perspectives, if you get if you already have it installed, or if you start new evaluation, it comes with a number of tutorials and examples. One of our tutorial is based on a data set that we use kind of everywhere, just sort of sample network data. We also have an example that ships with the software based on this Cineasts Movies and Actors database. And this is just at neo4j.org/develop/example data. And since both of those data sets are already out there and available for you to look at, you can kind of do that on your own time. And I figured today I would try something a little different. So I've made up, based on this Hubway Data Challenge data set, made up a little example that we can go through today and get the basics of what is Neo4j, how do I get the data out of it, what is Tom Sawyer, how do I get the data into it, and how do we get them to work together, right? So bring this up here. So if you've used Neo4j before, this probably looks very familiar to you. When you start up Neo4j, you can bring up a browser and just see what's contained within your data set, right? So this is the Hubway dataset example. And so there are four types of things in this data set, right? We have stations, which represent places where you can pick up or drop off a bike. Hubway is a local bike rental service. There are trips that represent where you go to and from and who made the trip. There are members who are people who rent bikes and go on trips. And of course, there are bikes that make those trips. Right? So you can create you can see what these look like, and they're all nodes, but they are also attributed, right? So for example, a member, if we view it in the table view, has the type member. It has a name. These data sets have all been anonymized, so this is birth year and zip code, right? They have gender, born in, and zip code, which are sort of duplicated in the name right now, just because of the nature of the data set. Trips are just trips. Bikes have a bike ID. And stations have a pretty good assortment of data describing them. So if we look at trips for a moment, you can see that if we double click on a trip here in the browser, it connects us to a station. That station has another trip associated with it. This trip has a bike associated with it. And this is sort of the arrangement of the data, right? So let's do a little query just to demonstrate that. So we're going to match a bike, which is on the bike label that I've added here. It's going to go through a bike edge type, and it's going to connect to a trip. And let's also find the member associated with that trip, right? So here is a member, and then we're going to return bike and member, and we're going to limit it to 25. So now we have a bunch of bikes and members. Oh, and we forgot to return the trip. So now it's not going to connect up for us. And here we go. All right, so this is sort of the nature of what the data looks like. Right, there are bikes that are associated with trips, members associated with trips. We can also look at, for example, start station, which is a start. And station is an end. And we're going to return start station trip end station. Oh, it's labeled in the wrong place. All right, so now we know trips are also connected to a station on each end through these start and end nodes, right? And start and end also has a date associated with it that describes when the project started and ended, right? So this gives us a good idea of what our data looks like. So now we know how to access our data through the Cypher query language. So now we're going to think about how to get that into perspectives. So what I have here is a project that I have defined in Tom Sawyer Perspectives Designer. Tom Sawyer Perspectives Designer is the visual design space that I mentioned at the outset that we were going to be working with a lot today. And we can turn the same types of queries that produced the data set that we just saw into an application where we can see all of that topology together very easily, and we can control the visualization to a much higher degree. This is a little bit sluggish because I'm presenting right now, but let's see if this will load for me. Sorry about this. We get a little bit of a lag on performance when I've got this presentation going. So let's just start with the schema and we'll go from there. All right, so in Tom Sawyer, you have elements that are defined by their model element types. Model element types are defined much the same way that they are in, for example, a SQL database. These allow you to define what your data is going to look like so that down the road, when we go to visualize it, we know what aspects of the data are important for the visualization, right? So when we looked at the member over here, right? So let's jump down and look at some of these members in the tabular form. We see that they have a name, they have a gender, they have born in, and they have a zip code. And so likewise, inside of our schema here, we're defining a model element type called the member that has a name, a gender, born in, and a zip code. And we're going to follow the same procedure for station, right? So station has a station ID, name, latitude, longitude, terminal name, installed, temporary, and locked. And if we jump up to the top here and look at this in tabular form, you can see here's our start station. It has all of these attribute names associated with it. Bikes just have a bike ID, and trips are somewhat interesting because if we look at a trip here, a trip has no attributes. That's not really useful to us in terms of setting up our data schema for visualization and perspectives. So we're actually going to do something a little tricky with it, which we'll get to when it comes to the point of writing queries. Right, so our trips, we actually want to know what they're connected to. So we want to know the start station ID, the end station ID, start date, end date, the member name, the bike ID for that trip, the ID of the trip, and a special attribute we're calling redundancy, which we'll explain momentarily. Right, so when you want to add data, right? So we have this Neo4j data. We have the schema that represents the Neo4j data within Tom Sawyer Perspectives. So now we need to tie them together. And the piece that does the tying together is called the integrator. So we're going to define the data source, right? So this is localhost 7474/db/data. If we look at our browser for our Neo4j data, it's at localhost 7074, and this is /browser. But this is the extension for the query. Right, so we just point it at the location of the data. We test the data source. All right, very cool. The data source is successfully running. Obviously, this doesn't have to be hosted locally. If you have a Neo4j database that is hosted somewhere on your network, you can access that. If you want to go out, get it from the internet, you can access that. If you have multiple Neo4j data sources, or if you have Neo4j data sources and other data sources that work together to give you your full representation of the data, you can also define multiple integrators. So if we add an integrator, it can be a composite, which means it's coming from multiple data sources. Database, which means a SQL-style database, an Excel sheet, Neo4j, an RDF data set, anything with a REST interface, structured text, XML, and anything else that you want to work with, you can define through the API level. Right? But for most things that people work with, they fall into one of these general categories. So let's jump in and look specifically at how we're going to get data out for Neo4j. So we have this match, just like we had before, right? So we can run basically this exact query. We'll just copy it, run it within our Neo4j browser. And we don't have this search defined right now, but we'll come back to that. And what we get back is a table, right? So instead of getting the nodes, what we need are the names, the genders, the born-ins, and the zip codes that represent all of the members that we're interested in. And we can see down here, if we run a little sample search, that it's going to come back and give us that same result here. Right, so here, because we have this search defined, that's going to give us an additional parameter. So we'll get to that in a minute, but it's not strictly necessary for understanding what we have here. So we run this query, we get back the members. Members are matching a search, and we're going to return member.name, member.gender, member.bornin, and member.zip code. These are the named attributes within the Neo4j database, and we're going to limit it to 15. Right, so down here we can see a preview in this database content pane that shows what we're getting back when we run this query based on current values against the database. And then we can go in and assign them, right? So it essentially forms a table for us, and then we assign it from within this table-like definition to our table-like attributed object model, again, similar to a database, or similar to a SQL database. But we are not porting this to a different type of database. This is just for the in-memory data model representation so that we can run the visualization on the front end. And we're very much doing the same thing in Station. But we have this sort of interesting complication because we've defined the search, and we still want to search on member.name. So we've got our match station that's going to connect to a trip, and then through a trip edge, it's going to connect to the member. And we are making sure that that name matches, and then we're going to go down and do much the same thing, where we have the station ID, station name, station latitude, station longitude, station terminal name, right? And assign these to these parameters. So very much the same procedure. Bike works exactly the same way. Again, we're connecting through a trip node, which is represented right here, through a trip to the member, and then we're checking the member name, and we're going to get back, a maximum of 50 bikes, and all we need is one column, so it's just bike.bike ID. Now, I said before that we were going to do something slightly tricky with trips, because trips in a Neo4j data, or in this Neo4j data set, right, represent something that doesn't really have a lot of inherent attributes, right? I mean, it's just a trip. And as a result of that, adding this type of object might not be terribly informative. Oh, there we go. Let's see if I can drag this down. Actually, I'll just go ahead and maximize it. So a trip really represents the connection between members, stations, bikes, and when all of those things coincide. So instead of having a bunch of individually attributed edges, what we're going to do is just bring that in all as a representation of what a single trip means, and this will be useful to us a little later. Right, so here we're going to do a slightly more complicated query. And if you're familiar with the Cypher query language, you'll see how this is structured. So we're going to start with the member. It's going to connect through a trip edge to a trip. That's going to connect to a bike edge to a bike. The trip edge, or the trip which is shared, so this trip and this trip, right, here and here are the same trip. And so we're interested in going from that same trip. We're going to look at the end trip to the end and the start trip to the start, right? And so we're going to, again, do the same match on the member.name. And then we're going to return distinct start station ID, end station ID, right? So we're actually assigning, this is from the start node station. This is from the end station node. This is from the start trip edge. This is from the end trip edge. We're going to return member.name as member name. So you can see that just like you can do return as in your regular Neo queries, you can use them inside of Perspectives when you're running your Neo queries, and your bike.bike ID. And we can also query the ID of the trip, right? Because as we saw in the browser, there are no identifiers except for the fact that it is this trip as labeled in the database. So internally, we need to find something to label it. It's not generally recommended by Neo4j that you use the database ID of an object. And so this is because they can be rewritten under certain circumstances, but because that's the only ID that we have available for this trip, we have to use it. Right, so members we can identify by the name, stations we can identify by the station ID, bikes we can identify by the bike ID, and these are all objects that even if there is some internal renumbering within the database, those attributes will remain unchanged. Right, and so again, we just assign each of these return values to a value that we have created within our schema. Right, so that's why under this trip we had all of these attribute types, even though a trip inside of the database is a very simple thing. So actually, while I am in here, I'm going to go ahead and reduce this number of trips because it does appear that I'm getting some sluggish performance during this demo. So I'm just going to turn that down so that this query runs a little faster and you don't get any issues. So let's start looking at what we're getting. So we defined this member query, and we have this search string, which we will talk about a little more. Let's just go ahead and run a desktop preview. So I have this search string, right? So right in my application here, inside of this view, I have defined this search string, which is looking for the name of a person. Obviously, this isn't the real name of a person, but female 1976 021 has 6 people in the database who nominally have this name, right? And this is where we are doing the heavy lifting, so to speak, turning the data that we have started here. We defined what a member was. We defined its attributes. We went into the integrator. We defined a Cypher query that we wanted to associate with our member data object. And then we found all these attributes and mapped them onto the attributes of a member within our data set. So now we have rules within our drawing view definition, right? So if I have views, I can create a new view, and I've created a drawing. And inside of that drawing, we have the definition, model rules, model element rules. So for my member model elements, right? So for every member I go and I find in the database, I'm going to undertake an action, which is going to be to add a node to the drawing. That node is going to be node.member.name, right? That's the identifier of that node. The template is going to be member, and the tags are going to be member. So templates, right? So this action creates a node, but we have to know what that node is going to look like, right? So obviously the nodes in Neo4j, they look like circles. That's essentially a template that they are describing, right? So this is a circular node. It's got the name in white in the center. It's got this sort of dark outline. We can define the same sorts of things in the designer. So we have this drawing template one, and I've created a template, right? So node, we're going to add a node template. And now we have this space where we can work that shows all of the potential attributes that we have associated with this fairly simple but highly customizable just shape. So, we can set from rounded rectangle to a pentagon, see what that does. We can set it to an up-facing triangle. We can turn off the gradient color, right? So now it's a solid. We can turn on glossy background, right? So now it's got this little shine on the top of it. So highly modifiable. Well, we've already set one up to represent members. So a member, we're going to represent with a rounded rectangle. We're going to set up some attributes here. So the name is what's going to be displayed in the middle. And here we're checking if the name exists. If the name is not null, then we're going to show the name. Otherwise, we're going to show the member name. And the reason we have this is because we can actually automatically generate any missing members from our drawing. And likewise, we're going to set the gradient color here so that if we're missing a gender, it's going to be gray, which just means that we're missing data for that node. But if the gender does exist and it's female, then we'll set it to be a pink node, and otherwise we'll set it to be a blue node. Right? Just pick some colors that people are going to be able to visually easily identify. So jumping back in here, we can run this preview. And now we're going and getting data from our data model. And here we have these 6 members. We'll do the same thing for a station, right? So here's a station. I've already predefined this, and this is just pause right now, so I'm just going to run it. Here's our stations. Our stations are ovals. They follow many of the same rules that we set for individuals. We're going to run it again. So now we have nodes that represent members, right? So we see their attributes down here when we click. We see that these green ovals represent our stations where bikes go to and from, right? So all pretty straightforward, just getting stuff out and viewing it. We're going to go again. So we'll add in bikes next. And again, I've already defined this, but it's just add a bike node, right? So let's actually go ahead, add a node, it's going to suggest node.bikeID. We're going to reference a template, which is just going to be bike. Okay, so I've duplicated this, but that's all it takes to create that add node action. Let's run that again. And so now you can see that we've loaded in some people, we've loaded in some places, we've loaded in some bikes, but now we need to figure out how all their connections work. And that's where trips come in. So we go down to trip, and we have add a trip node, right? So that's going to work exactly the same way as everything else, but where the interesting stuff is actually going to happen here is that we also have rules that set up connections between trips and other nodes, right? So now remember that when we set up our trips, we defined all of these interesting attributes that we actually defined based on the neighbors, right? So we know the ID of the neighboring stations. We know when the trip occurred. We know the name of the member. We know the name of the bike, right? So we have all of this extra information that we can now use to create connectivity based on this central trip, right? So let's go ahead and see how this is going to impact our drawing, right? So here we're just going to check if the bike ID exists and we're showing bikes. And we're just going to add a node if the node is missing, right? Otherwise, we're just going to create an edge. The same thing for members. And the same thing for start and end stations, right? We're just going to check if we're showing that object and the member name is not null. And then we're going to add an edge to represent it. So now you can see that we have something that's much more interesting. So this is a representation just in sort of a simple interconnected network layout view. It's showing the set of bikes. It's showing the members who rode these bikes, the stations that they went to and from. Let's go ahead and hit an orthogonal layout. You can see some of our nice layout technology. So now we have an orthogonally routed drawing. And we can use this to navigate around, follow some edges. This bike was used in that trip, also in this trip. Let's select a trip and see some of this nice information. And you can see that we have all this information here, but we also have a table down here that represents all the trips that we've gotten back from our queries. And since all of these elements are connected by a single backend data model, I can click here and find out about any trip that I want, and it will automatically show it in the drawing view. Right, so you can see that some of these edges look slightly different from each other. This is an edge that represents the start. This represents the end station, right? So this is the trip ID, the end station. We set this tooltip. This is the bike that's associated with the trip. So all bike connections are represented as dotted orange line. And the membership connections are shown in black, right? We can also use dynamic data filtering. So here we've set up these rules. So that I'm saying, if show bikes is equal to true, then I want to do this. Well, let's see what I've connected this show bikes attribute to this toggle here. We're going to turn off the bikes. We're going to turn off the members. We're going to turn off the stations. We can't turn off the trips because the trips represent all of the connectivity. Without those, it doesn't mean very much, right? So this kind of represents the baseline that you need to achieve and understand in order to really work inside perspectives, right? And so we have this drawing template that says what are our members going to look like, what are our bikes going to look like, what are our stations going to look like, what are our trips going to look like. We've got our bike edges that have this defined dotted line. We have a start edge, which is this green edge, and then we have an end edge, which is this red edge, and then we're just using a default black edge to represent our member connections. But it might be interesting, maybe we want our member connections to stand out in a particular way. So let's go ahead and create a new edge template. Let's call this a member edge. We're going to go ahead The direction of the connection is not very meaningful here, so let's just go ahead and select a straight undirected edge template. And maybe we want our color to be associated with the gender of the node, right? Just like we set up our nodes to have a particular gender color. So let's go ahead and see how we can associate the data of the trip with the edge that is being generated by that trip, right? So we have a whole bunch of functions here. These are a special expression language that is defined within Tom Sawyer Perspectives and that you can use to do things like make graphical customizations to define what characteristics you want. So let's say if a particular string, let's call it the member name, if it starts with F, then we're going to have this edge show up in the pink color, right? So let's call that 250, 100, 100. And otherwise, it will show up in blue, and let's call that 100, 100, 250. Okay, so now we've set an expression that defines the color of this edge. And now the edge will show up with that color. Let's go ahead into the definition, find the place where we're adding our member edge, and we're just going to go ahead and apply that template. So now our member edge template is available when I hit the reference button and I define my edge, right? So adding an edge is just like adding a node. You define an ID, you say what node it's going to come from, what node it's going to go to, and what template is going to be associated with it. And all of these can be referenced or suggested. Right? And now we can see that all of these incident edges on this female node, right, are coming in with this pink color that had been defined within that expression that I set. Okay. So the important things to understand here, and if you have questions, you are certainly more than welcome to ask them. It doesn't look like we have anyone who's asked a question yet, but if you would like to ask one, this would be a very good time to do it. We have Neo4j, which you work with using the Cypher query language, right, as a backend data source. You can add additional data sources if you wish, but for the purposes of show me your graph, obviously we're interested mostly in Neo4j. You say what the attributes look like. You connect those attributes based on queries. And then you define mappings from the data that you find, right? So for members that you find in your data, you're going to create member nodes. You're going to apply a member template, which you define up here. You define connections between your edges by adding edges, right? So add an edge from a source node to a target node. And you apply templates to the edges in the same way as the nodes. And you turn that from a query against your Neo4j database into a topology that you can view, either as this is a desktop preview in Java or an HTML5 preview in the web. Right, and so this is using, this is the same thing that we saw in the desktop preview, right? So we'll run them at the same time so you can compare, right? So we have drawing views here. We have a table view that represents everything that exists, all the trips that exist, they're all coordinated together. So I can make the selection here. We'll zoom in on it and show the details down in the inspector. And then we have this tree, which is setting up my controls, right, where I can do things like turn off all my bikes and turn off all my members. So one last thing that's interesting, and the reason that we created the trips in the way we did was that you are not bound to a single topology necessarily, right? So we can do the same things we did there. So we'll just go ahead and select in the table, zoom in, we'll turn off the bikes, we'll turn off the members. Let's turn off the stations, turn the members back on, see which trips they're associated with. And now we can get a quick count. Right, so we have this one very active member. Let's see if any of these members share bikes. So yes, these members have ridden the same bikes. They may be interested to know that. Perhaps not. Perhaps that's something they would rather not know, who's sat on the same bike seat that they have. But we could tell them if they want. But you can also use the single data model to drive definitions of views that are perhaps not the same. Right, so here we have a somewhat more complicated data view. And let's just see what it looks like. So here you can see that we have these green stations that look very familiar from our reference topology view, but there are no trips being represented here, or at least there are no trip nodes. What we have instead are edges that represent connections that have been made by the members that we have queried. So all of the trips here are in fact represented over here, but without the trip nodes. And we have some additional information built in. So these represent meta trips, as we're calling them. So this station is associated, so this station is the Kenmore Square station, and this is the Washington Street and Rutland station. And we can see that this edge here is green, while this other edge next to it is black. And the reason for that is that this trip has a redundancy of 4, which means there are four individual trips that started and ended at the same place made by these members. Right, and we can also see over here that this is a slightly lighter green, right, because that's redundancy of 2. And we can use our table to view around and see what our popular trips are. Right, so here's one that's a member of the 4, and anything with a redundancy of 1 is a unique trip that it was made one time by this member, but never again. So if you are looking at, for example, an aggregation of all the trips made by people from a certain zip code, you may be interested in what are the most popular trips. Are there certain one-way trips? So for example, right, it's not very common to go from Kenmore Square to Washington Street, but going the other direction is much more common. So perhaps that tells you something about the distribution of bikes that you need, or whether there is some usage pattern, maybe some time of day where that's true. So you can learn a lot by taking a single piece of data and in this reference topology view, it may be kind of hard to glean how many trips are going to and from a particular place because we have these intermediary nodes that sort of make each of these edges look unique, even though there are actually 4 trips here that we can see that connect in this way. And 1 trip, right, that's going the opposite direction. So the way we've achieved that based on the same single data set on the back end is by defining a trip not to be this sort of complicated, multi-stage, add a node if you're going to show the bikes, if you're going to show the members, then add all these nodes for bikes and members and edges to represent them. We've simplified that down to represent just a single edge that goes from the start station ID to the end station ID. We've set the source node to be start station, end station. We've applied a different template, which we've called the meta trip. And that meta trip uses the interpolate to color function based on the redundancy value that we've computed and the max redundancy which we've found. Right? And we'll take a look at those as well because computed attributes are something that can be quite powerful to use. Right? So inside of our trip here, we have this redundancy. We have this computed attribute. And inside of it, we define an expression, which is going to tell us what computation we're going to perform to find the value of that attribute. Right? So here we have the count elements function. Right? So we can go look that up. That's a lookup function called count elements. Here we have a nice box full of documentation that's going to tell us how that works. So it returns the number of elements of the specified types. If the parameters are given, then we'll only count those parameters that match those elements that match the parameter value. Right? So in this case, we want to make sure that we're counting all of the trips whose start station and end station IDs are the same as the start station and end station ID of the particular trip that we're looking at, right? So this will assign this redundancy value to each trip element. And then we're going to find the max redundancy at the model level by getting the maximum value in the list of all of the values that trips have for redundancy, right? So we're computing based on a computed attribute to find out what the maximum value for this particular item is. So in addition to that, we saw that we have these filters that we can turn on or off elements of the topology. And those are defined right down here. So we have very simple filters here. So we have this show members attribute. If it's true, we're going to let the members element types through for stations. If the station is true, then we're going to let them through, and we're also going to check that an element exists where either it's needed as the start station or the end station of a trip. Otherwise, we're going to hide it. It's just not useful to show stations that aren't connected to anything. And we're going to do the same type of simple filter on members that we did with bikes. Right? So this basically provides an overview of how you get that. We've defined these members, stations, and bikes filters right here. And that pretty much brings us to the end of what I wanted to cover this week.
Hey, Josh, there's actually a couple questions if you want to go through those.
Oh, sure.
You
the
see
questions
them?
did not pop up for me. So.
Oh, I can read them off. So there's one that came a little earlier from Marvin, and he asked if additional schema elements are added to the Neo4j afterwards, will the TS integrator still function?
Oh, so yes, the definition of your schema and your integrator only tell you what the subset of the data that's in the Neo4j backend you are interested in for this visualization, right? So obviously, we're only looking at a couple dozen nodes here in this visualization. Uh, this is a huge, huge data set that has I forget how many thousands of bike trips associated with it. But this is a very large data set. And if you want to add additional data types, so let's say, you had, if you wanted to add maintenance calls, right? So that you knew how often particular maintenance people were having to go to particular stations, right? And you wanted to add maintenance calls to your database, you would just add them to your database in the ordinary way. You would add a new type to your schema, and then you would add a new query to your integrator definition, and it wouldn't damage any of the previous work you had done. So you could just add it right in on top.
Okay, he said, got it. So, and then for the other attendees, I guess there's a questions box, there should be a questions in the control panel, or like there's a panel. So if you want, you can just type it in and we'll see it. And then there's one more question. It's kind of a three-part question, I guess, from
Sure.
Wolfgang. It says, where do you define the default search value? How are the filters defined? And is this interactive so you can type in a new member name?
Okay, sure. Yeah, so let's go over that. So I kind of glossed over this just because search is the search here is just being defined by an attribute, right? So this is just so that we get a smaller data set. As you saw, when you get these very large data sets, Neo4j will complain at you like it doesn't want to return these huge sets and then display them. It's best to keep your, just for performance reasons, right? You don't want to attempt to run a query that's going to take 3 minutes to return because you're trying to find 30,000 data objects based on some parameter, right? So you want to narrow that down, and what I've chosen to do that is to define the search text model attribute and just given it a default value. And we can actually see the value of that search text right here. So here's the member search. And we can even change it somewhat. So, if I change it from female to male, we can then update the integrator again, and it will get us an overlapping but different data set.
Okay.
It may be that change didn't actually change the result, just because that was like these were the first results and it already had these queued up. But maybe you can change it to like male 1977. It looks like this is doing something a little bit different right now, but I'll have to look at that in detail. But fundamentally the answer is that yes, this is modifiable at runtime. This is just an attribute, just like the show members attribute. And these are all just attributes of the model. There aren't multiple instances of them. Like we have a whole bunch of members, we have a whole bunch of stations, but we just have one thing that's controlling whether we're going to show the stations, one thing to show if we're going to show the bikes, one thing if we're going to show the members, and one search text string that is allowing us to search on members on the back end. And inside of our definition here, we have this where member name equals search text. And search text in these curly braces here is actually telling it to insert the value of this search text parameter that we've defined here within quotes. So this is, we're going to do a string concatenation. We've escaped this character here and this character here because obviously parentheses are special characters within this expression language. We have this question mark I in parentheses that defines the that says that we're going to ignore case for our search text string. These are wildcard characters, these dot stars here. Right, so this is all just Cypher query language. And then we're going to use the value of search text within our model, right? So this is the value of the search text model attribute, right, that we've defined right there. So actually, if we jump in to the Neo4j browser, right, if we say this, let's see. Let's see. And we'll do it like this. So we'll just add in this same expression. So we'll do member.name is equal to approximately this search string, right, where that's question mark I dot star, and then in here we had female 1976 021. Right, and so this is running this query. This has gotten the same data back that we are seeing in our query. But obviously, instead of having this Neo4j graphical drawing, we have the Tom Sawyer Perspectives version, right, which has different layout options, right? So we can do a hierarchical layout, which shows a flow between them. We can do a symmetric layout, which is a lot like the Neo4j symmetric layout, and an orthogonal layout, which is the schematic view, right? And of course, circular view, which is where we started, which shows clusters within the data.
Great.
So
He
that's
said
just
he
just
got the
modifying our
principle.
Cypher query.
He says, okay, got the principle, thanks.
Okay.
So looks like there aren't any other questions coming in, but I'll send an email out shortly to attendees so that they can get the recording and then sign up also for part 2 of the webinar if they're interested. So they'll get all
Yeah,
the
and in
information.
part 2, we're going to be talking a lot more about some of the more advanced interactive features, such as searching the data once you've loaded it from the database, refining the way that your front end looks, adding custom actions for data exploration, and pretty much taking this, which is a very bare bones framework, and turning it into a much nicer visualization with much nicer interactive capabilities.
Okay, sounds good. So thanks so much, Josh. And if anybody has any questions, then I'll send an email out shortly. Feel free to respond to it. And thanks for attending.